This video lecture is meant to explain some of the additional problems that were on the Unit 3.3 through 3.6 unit review questions. And so let's take a look at Unit 3.4, which was Graham's law and Dalton's law of partial pressure. So there's a problem. We're looking right down here. The additional problems here, number one, you have 888 milliliters of oxygen gas that are collected over water with a temperature of 25.0 degrees Celsius. The total pressure of the gases, plural, gases, is 55.8 kilopascals. What is the partial pressure of the dry oxygen gas? So just to give you a visual to see what this is going on, this is my very rough sketch of, okay, so here you have a flask that there's a chemical reaction going on in there that's producing oxygen gas, which I'm showing you here is yellow, just so it shows up. Oxygen gas is actually a colorless gas. So this yellow gas is piped through this tube and into this container, which is very crudely shown, but this is an upside down beaker that has water in it. And as the gas rises up through the water, that's what these bubbles are, the gas will float to the top because it's less dense and water will be pushed out. So we can be fairly certain that the only thing that was in here is the oxygen gas because this beaker would have started full of water. So the oxygen goes up and the water gets pushed out. So we know that this volume, this 888 milliliters of gas up here, is oxygen gas, but we also know that it contains some water vapor because at all temperatures water will evaporate. So we are going to use Dalton's law of partial pressure to figure out the pressure that's exerted by just the oxygen and we're going to subtract out the pressure exerted by any water vapor. So that's the P total is equal to the partial pressure of the oxygen plus the partial pressure of the water. We know the total pressure is 55.8 kilopascals. The partial pressure of the oxygen is what we're trying to figure out. And this number here, this 3.17 kilopascals, this number comes from, you could either interpret it from table H, this vapor pressure of liquids, or if you notice there's a little bit more detail in this chart down here, table H-1. At 25 degrees Celsius here, the pressure from water vapor is 3.17 kilopascals, or kilopascals, kPas. So that's where this number came from. And so just by simple subtraction and maintaining significant figures, we see the partial pressure from just the oxygen is 52.6. What you will notice is that the volume of the gas, being 888 milliliters, was extraneous information. It doesn't make any difference in terms of the pressure. How much water was there to begin with. It's only dependent on the temperature. So if we take a look at the second additional problem down here, this is still section 3.4. This is a Graham's law. How much faster will hydrogen gas, H2, with a molar mass of 2.0 grams per mole, how much faster will that diffuse compared to chlorine gas, which has a molar mass of 72.0 grams per mole? So let's go ahead and take a look and see where these numbers came from. H2 from the periodic table has a mass to the nearest tenth of 1.0. Okay, and so since the formula is H2, we take that 1.0 and we double it because there's two, so hydrogen H2 will have a mass of 2.0 for every 1 mole of it. Okay, that's what the molar mass means. It's the mass of 1 mole. And that's what this subscript will tell you to do. Now chlorine, if you look on the periodic table, to the nearest tenth is actually 35.5. That 4 has to be rounded up. And so since chlorine gas is Cl2, it's diatomic. So doubling 35.5 is going to give you 71.0 grams per mole. And of course, that's to the nearest tenth. Right? So that's where we're getting the masses from. We will then plug those into the Graham's law equation. The comparison of the rate of gas 1, in this case hydrogen, compared to the rate of gas 2, in this case chlorine, is equal to the molar mass of the second gas, in this case Cl2, divided by the molar mass of the first one, which is hydrogen. So we have 72 divided by 2, which is of course 36. We take the square root of that and that equals 6. So what that means is the rate of gas 1 is 6 times faster than the rate of gas 2. So the smaller molecule always travels faster. In this case, if you had to be quantitative and say how much faster, you plug in these masses to give you that ratio. Let's turn our attention now to 3.5, which was the gas laws, and we're going to see a bit more complicated questions just beyond the combined gas law and involving Dalton's law of partial pressure. So if we scroll down the review down to the additional problems right here, these require the use of Dalton's law of partial pressure, table H or H-1, and the combined gas law. So for the first problem, we have 1.000 liters of hydrogen gas. It's collected over water, similar to the first problem I just showed you. The temperature is 30.0 degrees C at a pressure of 110.9 kilopascals. Right? So that's the initial set of conditions for the gas, but it's not just the hydrogen gas, it's also hydrogen gas mixed with water vapor, and we know that because it's collected over water. We then need to find the volume of the dry hydrogen as if it were collected at standard temperature and pressure conditions. So STP will be the new set of conditions that we're going to convert it to. So this is an equation that we're going to rearrange for the new volume, because that's what this problem said, find the volume collected at STP, that's V2. So rearranging for V2, we get this equation right here. Defining all our variables, T1 was 30 degrees Celsius, so 303 Kelvin. T2 is 273 Kelvin. We get that from standard temperature and pressure. Standard temperature is 273 Kelvin. V1 is the 1.000 liters as defined in the problem. The initial pressure, which I'm calling here, it's the wet pressure at 110.9 kPa, that number was given to us. Okay, so we're going to have to modify that number before we directly plug it into the combined gas law, but we'll come back to that. P2 is our new pressure. It's going to be standard pressure, so 101.3 kilopascals. Okay. Now before we can plug all these numbers in to the appropriate places, because you'll notice here's the 273, here's the 1.000 liters, here's the 101.3 kilopascals, and here's the 303 Kelvin, but the initial pressure that I plugged in is not the given pressure. So if we take a look, how did we account for the water vapor? Well, that's that Dalton's law of partial pressure. So P1 is 110.9 kPa. It's the total pressure of the H2 gas and the water vapor. So you've got to use Dalton's law of partial pressure to find the pressure of just the dry hydrogen gas. So total pressure wet is equal to the dry hydrogen plus the pressure of the water. So there's the 110.9 kPa is given. That's going to be equal to the dry pressure of the dry hydrogen. That's what we're shooting for. And then this number, if we take a look, we have to look at that original temperature of that water at 30.0 degrees Celsius. Well, that's not on this chart, so we're going to have to interpret it from the actual graph. Now, it's this graph right here that is the water, so if we focus at 30 degrees Celsius, okay, so here's 25 degrees Celsius, here's 30 degrees Celsius. So if we read up right there, that's, if you read over, that's about 5 kPas right there. So that's where this 5 kPa comes from. And then we subtract out to get the dry hydrogen pressure right there. That's the 105.9 that we're going to use as our initial pressure, and then you go ahead and solve and you find your new volume that way. The second additional problem here is essentially the same type of strategy. This number 2, 6.12 liters of wet xenon gas. Same strategy, so I'm not going to spend the time to go over in detail. I'll let you take a look at the answer key up here. Hope that it helps clarify some of these more complex questions. And shoot me an email if you think you have more questions. All right, you guys, you're going to do great. Hang in there. See you soon.